And people estimate that if we continue using energy the way we do today, it's going to go really bad in terms of global warming, etc., etc. Some people object to the idea that it has any impact, but if for nothing else, it seems to me that by looking at the figures on the right-hand side, that we're perturbing the system, changing the conditions on the planet in ways that are different from what happened over the last 1,000 years. And even if people feel that there may be more in play than just us burning fossil fuel, I think it's a good idea just to return the planet to the next generation the way we received it from our parents. So something needs to be done in terms of emissions of greenhouse gases. And the reason why we see this abrupt change is that we started clearing our forest and we fell in love with fossil fuel. It's a very convenient way of transporting ourselves around, etc. But also from just constructing buildings using cement. Cement production produces a lot of CO2. And it's now higher than what we've seen for the last many 100,000 years. Okay? So obviously there will be a potential impact if we start changing the composition of the atmosphere. And we need to act fast to avoid having to deal with the consequences of not knowing what we're doing. So the current emissions, the amount of CO2 that we emit a year is roughly 24 gigaton per year. That's a big number. And if we were able to just grab that CO2 and store it somewhere at a density that is half of water's density, that would amount to 125 million barrels of CO2 per day that we would have to stick somewhere. Okay? In comparison, the world's oil production is roughly around 80 million barrels a day. So storing 1/6 of our emissions is at the same scale of operations that we're doing today by pumping oil around in pipelines, in oil tankers, etc., etc. The big difference is that you don't get as much money for the CO2 as you get for the oil. So what are the options to reduce emissions if we need to start handling these big amounts of CO2? Well, first of all, we can emit less by increasing our energy efficiency. We can try to capture and store it somewhere, as I alluded to in the previous bullet. And then, of course, what we're already transitioning into is new and less CO2 intensive energy sources. I'm pretty sure this number is reasonable actually for the day, but we're sort of around 85% fossil fuel based energy today. So there's a lot of work to be done to switch to less intensive, CO2 intensive sources. So the overall message I'm trying to establish is that there's no silver bullet, and we need all efforts available to try to tackle this problem. Okay. Now, if we look at options for storing CO2 in the subsurface, in geological formations, there are three sort of prime candidates. One is in depleted oil and gas reservoirs, and another one is in unminable coal beds, and the third one is deep saline aquifers that are not useful for drinking water or any other purposes. And this figure shows estimates of how much CO2 we could store in each of these three candidate storage sites. And there are two sources of data. One is from the International Energy Agency, and then one from Parson and Keith in a somewhat old paper now, but the actual numbers are not the most important part. The difference or the span of the estimates are the most important part to notice in my mind, because it suggests that we don't really know. If you can store between 370 and 1,100 gigatons of CO2, it would be nice to narrow a gap like that down a little bit. The most extreme is, of course, if you look at the lower right-hand side, where you see CO2 storage potential in aquifers going from, in the red numbers, one source, 370 gigaton to, in the upper part, 10,000 gigatons of CO2. So a range between 20 to 500% of the oil emissions up until 2050. So we need to narrow that down a little bit to convince people we know what we're doing. So, one of the big questions that we need to be able to answer if we want to try to tackle this by storing CO2 in the subsurface is to understand where any CO2 that we inject in the subsurface end up. And I'll show a little picture here of a sort of a accumulation of CO2 vapor it could be an oil and gas reservoir, but in this case it's a storage aquifer, where we have an arrow on the right hand side where we inject CO2. CO2 is sort of pooled up underneath an impermeable cap rock, and somebody drilled a well there at some point for drinking water or something and forgot about it, so there is a potential leak path for CO2 to get back to the surface. And those of you who live in California are familiar with faults also, which is a potential leak path for CO2, because once we start changing the stress in the subsurface, we may activate faults, and that will potentially allow CO2 to escape back into the atmosphere. So, to understand all these things, we need to combine efforts from engineers, geologists, geophysicists, etc. So it's really a multidisciplinary effort required here, and there's a lot of good research going on already, but there's still a lot of work that needs to be done. So, the outline of the rest of my talk is sort of three different categories. One is CO2 in oil and gas reservoirs. I'll start by just give you an idea about what it is and how it works. And then I'll talk in more detail about CO2 storage in aquifers. And then I'll talk about CO2 in coal beds. And then summarize some research challenges ahead. There you go. So we start with the oil and gas reservoirs. Now, enhanced oil and gas recovery. Why do we need it? Well, I'm sure you heard some about this earlier in your program. But if we produce oil by natural energy sources that are in the reservoir, you can potentially get as much as 10% of the oil in place out. And then if you move into a secondary recovery phase where you try to displace oil in the subsurface by water, you can probably recover another 25%, sometimes a little more. So at that point, you still leave a tremendous amount of oil left back in the subsurface. And that's why tertiary recovery aims at recovering or producing what is left behind by primary and secondary. And one of the reasons why CO2 is very useful for this is that if you inject CO2 in the right oil at the right conditions, that is temperature, pressure, etc., you can really get an efficient displacement of the oil that is left in the reservoir, and you can recover significant reserves in addition to what you get from primary and secondary. So in the US, enhanced oil recovery is accountable for about 800,000 barrels a day out of roughly 5 million total. And if we look at how that is split up in different ways of different methods of enhanced oil recovery, CO2 injection is accounting for 200,000 barrels a day, primarily in Texas. Hydrocarbon gases, such as methane, ethane, etc., accounts for an equal amount, about slightly less than 150,000 barrels, mostly on the North Slope in Alaska. And then finally, steam injection, which is also a method of enhanced oil recovery, is used to extract heavy oil from the subsurface in California and produce roughly 450,000 barrels a day. So, if you want to summarize what is enhanced oil recovery, really what it means is that you inject something into an oil formation that is not initially present. So that sort of distinguishes from improved oil recovery, but sometimes people debate what it is, what is what, because steam is water, and water is typically always present, but it still counts as an enhanced oil recovery process. Now, here I show you a little map of some of the successful applications of CO2 injection for enhanced oil recovery in Texas. It's called the tri-state corner, whatever they call tri-state corner in Texas. And they started in the 70s by injecting CO2 into the subsurface. Unfortunately, what they used was CO2 from naturally occurring sources, they have some accumulations of CO2 in the subsurface of very high purity that was in some of the domes that are in I think it's in New Mexico. Oh, sorry, it is in Texas actually. And they pump around a significant amount of CO2 already in the infrastructure that's depicted on the right-hand side. Now, in 1998, that's 10 years ago, and the number has increased significantly, but not that, not to change the fraction of what of what we emit significantly. So if you inject 7.5 million ton a year of carbon, that only accounts for 0.6% of the global emissions of CO2. So we need to have many more Texas scale efforts around if we want to take care of reducing CO2 emissions by CO2 EOR alone. Okay. Now, let me show you a schematic. You've probably seen a similar one earlier. You have an injection well. Can you see my mouse also?
Yes.
Okay. So, all right, good. So I can move around a little bit. So we have a well where we inject CO2 into the subsurface, and it sort of displays oil in the porous material that is down here, and it drives it towards the production well, and then of course you manage to bank up additional oil that reaches the production well before the CO2 if you're lucky. But sooner or later CO2 is going to reach the production well, and then you have to modify your operations, potentially use separation processes on the top side and recycle CO2 back into the subsurface if possible. At a much, much smaller scale, if we look at an image here, this is known as a micromodel. It's basically a glass model that has this pattern etched into it and then it's been sandwiched so it creates the porous material. And what you can see is you have some channels with dark color, which is oil, and then you have injected CO2 on the left-hand side for a while, so it has created this triangle where all the oil has been displaced. You produce from the right-hand side, and the idea here is that if conditions are right and the oil is appropriate for compatible with CO2, you can really displace and remove a lot of the oil. Where in this case, where the CO2 went, all the oil is gone. Okay. Now, and the reason why it works is basically due to phase behavior or thermodynamics, and it's due to the fact that CO2 is a very good solvent. It extracts some components from the oil and carry the sort of enriched gas forward, and at some point it manages to create a single phase composition that basically moves all the oil out of its way. So it's a very efficient way if conditions are right. Unfortunately, this is only half of the story. Where CO2 go, oil is gone. But what about places where CO2 doesn't go? Keep in mind, CO2 is a gas, and although we can compress it to a very high density, it will typically be less dense than the oil and have a tendency to climb upwards due to gravity differences. In addition to that, it has also a very low viscosity, meaning that it is likely to create what is known as viscous fingers, essentially an instability of a front, and all of a sudden you will have fingers of CO2 moving faster than the main front, and you will not be able to contact the entire porous material. Now, so much for CO2 EOR. If you have any questions at this point, I'm going to switch back and look at the picture view and see if anybody waves their hands.
Okay, we do have a question.
No questions?
One question.
I see one.
Okay,
go ahead.
I have a question about the CO2 injection. Would it be possible to do the CO2 injection thing and then displace the oil and then underneath the surface convert the CO2 to CH4 and use the leftover H2O for the steam injection thing?
So I have a difficult time hearing.
Oh, sorry.
you left.
Okay.
Can you please repeat the question? I didn't hear the last part.
Yes. So I had a question about the CO2 injection thing. So could you inject CO2 and that would displace the oil, and afterwards underneath the surface, like convert the CO2 to CH4 and use the leftover water to like start the steam injection thingy? Does that even make sense? I don't know. I'm just so curious.
Well, I mean, it's a good idea. The problem is that to convert, you know, to put hydrogen back on the carbon in a methane molecule, you would use a lot of energy. See, because what we do is we take methane and we add oxygen, and then we produce CO2 and water and get energy out of it. So what you're suggesting is you want to do it the other way, where you put hydrogen back on the carbon molecule. Unfortunately, you can do it, but it costs you a lot of energy, so there wouldn't be any gain in that way. It wouldn't unfortunately solve the problem, unless science allows us to design some very efficient catalyst that can promote this. It's not going to be. It's not going to do the right thing. The natural direction of this process is that you take the methane and you combust it with oxygen to create energy, and so you get CO2 and water out as the product of that.
Okay.
But it's a good idea. If you can turn it around, that's why we need young bright people like you to try to pull off these type of things. Okay.
Any other questions? Okay.
Any other questions?
We have one more. I think that microphone's pretty good.
Okay. One of the big concerns.
Go ahead.
One of the big concerns with CO2 injection is the CO2 leaking. Is there any sort of solution that we have right now to prevent that from happening?
Solution, well, what people will talk about is that we need to monitor when we inject CO2 or any other gas for that matter in the subsurface. And there's a lot of activities going on using seismics, shooting seismic, getting seismic images of the subsurface repeatedly in time to try to understand how or where the CO2 is going. I'll show you some examples of, I'll show you some slides later on why it's very difficult to guarantee that CO2 never escapes. Basically because we have, in the US, a lot of wells have been drilled over the years that penetrates the seals that would prevent CO2 to escape. And that has been going on ever since they started producing oil many years ago. And people have not really kept track of where the wells were when they abandoned them. But let me return to this. I think the right answer at this point is no, there's no solution. There are techniques that allow you to monitor where it goes. It's a costly process, and people are working towards cheaper solutions that will allow you to understand if CO2 is leaking or not. Okay?
Okay, no question. We'll go to Garrett in the back first. Garrett, he's got the mic right behind you.
With the CO2 injections, are we hoping that the CO2 will change into something else under the pressure, or are we just hoping that it stays CO2 and it stays underground for many years to come?
That's a very good question. The key idea, the initial thought is that if you have a reservoir where that doesn't leak, that's sort of the ideal setting in any way. CO2 is going to stay CO2 primarily for the first period of time, and then if there's any water present, CO2 will dissolve in the water and form this carbonic acid. And that can cause other geochemical reactions where you change the pH of the system, and some of the minerals that are in the subsurface can react and create new minerals, and that way CO2 is gone forever. It's not clear that the amounts that we would need to inject if we want to do a serious impact on emissions, if that will have the opportunity to react and create new minerals, etc., etc. So a portion of what we inject will potentially stay as a immobilized CO2 phase forever. But there are options, there are potential for conversion of CO2 into other either other minerals essentially, or as dissolved as a dissolved component in the brine that is down in the subsurface. I'll actually return to that a little bit later when to talk about time scales. How long do we need to look, and when do we estimate various processes to take place, such as geochemistry, etc. So let me get back to that once I reach that slide in my presentation. Okay.
Yeah.
We have another question, Sybil. I think your mic's pretty good.
How costly is it to pump CO2 back into the depleted oil reservoirs or underground?
Okay. Yeah. So it varies a little bit, but on the, I think I have, if I back up one slide here, let's go back here. Okay. Basically, if you look at they basically, when people try to assess what the cost is, let me rephrase that. When people try to assess how much CO2 we can store in the subsurface, there's also always an economic factor that you need to look at. And for instance, when the International Energy Agency looked at potentials worldwide, they assumed that it would cost $20 to inject 1 ton of CO2 into the subsurface. Now, of course, if you inject that CO2 into an oil and gas reservoir to increase your recovery of oil, that means that the expense for injecting is going to be, offset by you selling the incremental oil that you produce in that operation. If, on the other hand, you want to inject it into basically salt water in the subsurface that nobody wants to buy, then the price is still $20 a ton of CO2. It may fluctuate depending on who estimates it, and so if we choose to inject the bulk of the CO2 into an aquifer, then it's going to become a very expensive operation if you need to inject multi-gigaton of CO2. You can see how that scales. If you multiply that by $20, then somebody needs to pay. Right?
Liz, did you have a question?
Yeah, I did. I know you mentioned converting CO2 into something else. Another possibility that's come to us is converting CO2 into methane. Do you believe we have the technology now to actually make methane a reliable and stable source?
It's not a feasible solution at this point. Simply because the way that you create CO2 is by burning methane, for instance. And if you want to go the other way, you lose, because thermodynamics will, there's some principles of physics and conversion of matter, or let's call it thermodynamics. It's essentially saying you will always lose when you convert, to, let's say, methane to CO2. And if you want to try, is the natural direction which nature's is sort of interested in trying to do. If you try to do it the other way, you will always lose. What you would need is, you would need to, well, you can do it if you can use solar energy, you can use other things, but at the end of the day, you would lose because you would need to handle, you need to collect CO2, you would need to do things. You could potentially do it, but I'm pretty sure that the energy balance would not be in your favor. You would potentially spend more energy doing it than what you would end up having in your methane source at the end of the day.
Okay, thank you.
Okay, and then Vince, you might need the mic. Prasad?
Yep.
For a minute?
So sorry.
Right, for now we've been talking about just using CO2 as a gas for sequestration, or just putting it in under or subterranean, places. But I was wondering that would it be cheaper if we converted or tried to at least put the CO2 in water first or as a solid before we put it underground? Is that a viable way to do it?
Well, you can do that. You can try to do that too, but that would essentially amount, this would amount to injecting Coca-Cola somewhere, essentially. And the problem with that is that the amount of CO2 that you can dissolve in brine is not a lot. I think it's, how much is that? 5–10% CO2 you can dissolve in water, depending of course on temperature and pressure and so forth. But the bottom line is that the volumes that you would have to handle if you try to dissolve CO2 in water before you inject it or do something else with it, is going to increase significantly. Over using a pure stream or as pure a stream of CO2 as possible. So the infrastructure the capacity of the infrastructure would increase significantly if you don't inject pure CO2. People have tried some experiments where they use carbonated water, etc., but at the scale where we're looking at things here, if you really want to try to get rid of CO2, you need to work as pure streams as possible of CO2.
Okay, thank you.
I was just wondering, how do you collect the CO2 in the first place? Do you use a vacuum or something?
So what people do is, this is not my field, I don't do the separation part of it, but let me give you an idea. There are different technologies. What people do is, for instance, if you have a coal-fired power plant, they can either use some membrane technology where you can separate gases such as nitrogen and CO2 and produce a more pure CO2 stream. You can also use basically you use well, it's basically absorption columns that they use. So what you do is you bubble CO2 through a liquid. Well, if you have, let me do this differently. If you have a mixture of nitrogen and CO2, and you bubble it through a liquid where CO2 dissolves much better than nitrogen, you can create a concentration of CO2 in the liquid phase. And then later on what you do is you regenerate the liquid phase by changing the temperature essentially and boil off whatever CO2 that you had in the liquid. And that allows you to separate the two. But it's a very active area of research, unfortunately not mine at this point. But people are working at developing membranes that allow CO2 to get through and nitrogen not to get your good separation product. So that has to do, again, all of this has to do with thermodynamics and characterization of porous materials, all the wonderful things that chemical engineers are doing. So we need good people to come up with good separation processes.
Thank you.
Okay, any more questions?
Not at this time.
Not this time. So I can see that we're running out of time fast. I have another 3 minutes, right?
Yes.
Okay, and I have another, let me see, 25 slides. So that's not going to work. So let me do this. Why don't let's talk about CO2 storage in aquifers, and then I'll do that briefly, and then I'll skip to the summary of some of the challenges that society is facing these days that you will be able to help out solving once you continue your education. Okay. So we talked about this a little bit already. Some of the key questions when it comes to storing CO2 in the subsurface and in aquifers in particular. Basically, how far does CO2 go? How long does it take before it stops moving? And what fraction of the CO2 that we put there can escape? In trying to answer these things, what people do is they use models where they try to predict the behavior of CO2 as you inject it in the subsurface, and come up with ideas about how long does it take, how far does it go, and what is the risk. Now, let me move on. An example here, I'm not sure whether you've seen this before. It's one of the big demonstration examples of storage of CO2 in the subsurface it's offshore Norway, the Sleipner field, they call it. It's been going on for many years now, and it's operated by Statoil. And essentially they separate CO2 from oil and gas that they produce, and they inject it in the subsurface above where the oil and gas is. Okay. Now, the main thing here that people are trying to answer when they look at this option for storing CO2 is what are the timescales for various physical processes, in favor and against, long-term storage, and they're summarized there. I'm gonna flip to the next slide to show you what happens here. So if we look at the timescale, it's basically running from day 1 to 1,000,000 years, essentially. Now, the injection phase where we store is potentially, it's going to go for tenths of years, maybe maximum hundreds of years, if we have a really large aquifer. And then you stop injecting, and what happens then is what we call the relaxation phase, where differences in density between brine and CO2 is going to create movement of CO2 upwards in the formation. At the same time, capillary pressure, which is essentially what you see when you try to get water out of a sponge, and you have to squeeze it to get out, it's not coming out by its own, is causing CO2 to become trapped in the porous material below too. Some of the, yeah, it's not my baby boy just woke up. Mommy's going to try to stop him, and then it's my turn afterwards. so anyway, so the idea is that there's a big difference in time scales between different physical mechanisms that's going to help us store the CO2 in the subsurface. In particular, geochemical reactions have been estimated to span, it can start after 50 years, because they're very slow reactions, and they can last and run for tens of thousands of years. So the point is that people are trying to simulate what is going on, because obviously we cannot do experiments for tens of thousands of years because we won't be around to see the result. So we rely on models and interpretations of the physics to try to estimate how long will it take for CO2 to react. First it dissolves in the brine, and then it reacts with minerals, and it can either create more volume of solid, or it can create pathways for CO2 to escape if it eats up some of the materials in the subsurface. So people are really struggling with trying to come up with good estimates of how long does it take for CO2 to stop moving and stop changing things in the subsurface. I'm going to skip properties. This is basically just no, it's not worth it. Let me show you an example of some of this modeling work I've been involved in. It's basically we're trying to inject CO2 in the subsurface in a 4.5 kilometer by 4.5 kilometer by 160 meter portion of the subsurface. And what we can see after 10 years of injection, we compare different ways of simulating it. One is called FD and one is called CS-LS. And what we were trying to do is come up with efficient ways to predict the movement of CO2 in the subsurface that will allow us to do many calculations so we can use statistical approaches to estimate how far does it go. Okay? And basically I compared with a more conventional time, and it turns out that our approach is an order of magnitude faster, which is very good. Now, after you inject things and you stop, as I mentioned, CO2 is going to move around, and then the question is, what happens after, if you just let gravity move the fluids around and redistribute them? There are two different scenarios. One is called hysteresis, and the other one is called non-hysteresis. And that is related to how we choose to model the physics that we believe takes place. People do one or the other, and as you can see, there's a tremendous difference in the distribution of CO2 in the subsurface depending on how you choose to model it. So what people are trying now is to do small-scale experiments and try to model what they observe, and then build confidence in our predictive capabilities and our understanding of the physics as such. I'm just going to skip this one. Oops. Here's a picture of what happens in long term. The question is, do we really understand what happens when you inject CO2 into the reservoir of rocks or the porous materials in the subsurface? As I mentioned, once this CO2 dissolves in the water, you end up having a reduced pH. And if you have carbonates and things like that, you can dissolve the materials, and you can start having these wormholes forming in the porous material. And if that goes on for long enough, obviously that will create a pathway for CO2 to leak back into your neighbor's basement or back to the atmosphere. So we need to improve our understanding of these things before we proceed at large scale with these CO2 sequestration efforts. Let me skip through here and wrap it up, because this is another type of physics which is somewhat related but different. And just look at the big question: world war integrity. We drill wells to place CO2 in the subsurface, just like we drill wells to produce oil and gas, and also for producing drinking water sometimes. When we drill holes through the subsurface, we penetrate all the seals that will help us keep the CO2 in the subsurface. And of course, if we abandon them without closing them off appropriately, they will be pathways for CO2 to leak back. Okay? And in many places, you have old wells that was left behind and not securely tightened before they were abandoned. In old days, they used everything from telephone poles to other things to close an old well and then assume that everything was fine. The state of these abandoned wells and the location must be known before we can say anything about uncertainty, etc. Let me show you a slide here of, this is from Kansas. This is a map of Kansas with abandoned wells since 1996. Okay? These are wells that have been plugged since they started saying we need to pay attention to this because the subsurface needs to be sealed off from the atmosphere. Right? And this is just the wells that they have found and plugged since 1996. And it looks like a needle cushion, pretty much. and so does the rest of many other places of the US where we're thinking about injecting CO2 in the subsurface. So the challenge of finding these potential leak paths, ensuring that they're appropriately closed, is a tremendous task. And the different states are working by different mechanisms to ensuring that these are located and found. But some of them are very old and very difficult to find, and they may be even somewhere in your backyard. So let me show you the last little somewhat scary story, unfortunately. It was about a natural gas storage project where they injected gas in the subsurface for storing it, and you can see the top image on the right hand side is sort of an image of the geology where they try to store gas in the subsurface. Now the problem was that one of the there was a leak in one of the wells, and the gas started migrating up the well, and unfortunately the geology was such that it could climb uphill and accumulate under the little town of Hutchinson. And the problem is that one of the wells leaked an old well leaked in the town, and we had a gas explosion that killed some people, which is a very sad story, but and a very good indication also that we need to be very careful when we start injecting things in the subsurface, because they can seriously end up in somebody's basement or backyard where you don't want to see it showing up. Okay. So, in summary, we have the capacity, the storage capacity, to do a serious impact of the emissions if we really want to. Okay. Unfortunately, so does the number of challenges that we have in front of us in understanding where the CO2 is going, what the consequences are of injecting it into the subsurface. So there's a lot of research and a lot of jobs ahead in trying to understand and improve the security of these type of operations if we're going forward at large scale with storing CO2 in this fashion. The saline aquifers are probably the best candidates because they have a large storage capacity and they're available in many places. The problem is that oil and gas reservoirs are not necessarily available at every coal-fired power plant, and so looking for aquifers seems to be a good opportunity from big point sources at least. The good news is that the infrastructure exists for oil and gas reservoirs, so that may, and in my opinion, should be the first place where we look for storing CO2 in the subsurface, because we will still need fossil fuel for some years to come, and why not utilize some of the CO2 that we try to sequester to improve our recovery of the existing reserves in the subsurface. Another thing is the big challenge that we face is how do we estimate potential leak rates when we start to do this. And many people are working on it, and many people will continue to work on it for many years to come up with good answers and good tools for estimating what is the potential of any CO2 that we inject to get back. In addition to that, we need to understand what is an acceptable rate of leakage, because most likely it will be impossible to guarantee that CO2 stays in the subsurface forever. But if it leaks back at a very low rate over many thousands of years, it may not have an impact at all. On the other hand, if it all comes back very fast, it may, as you showed for the gas explosion, have some unfortunate consequences for people living in neighborhoods where CO2 is injected beneath the surface. So overall, there's a lot of research, good research challenges ahead. There's a need for a lot of young people like you to pick up the ball, start studying these things, and help solving some of the problems that we're facing these days. So I hope that you can take some of the ideas here and think about it a little bit, and potentially look in this direction when you decide for graduate studies down the line, because there's a lot of fun and challenging projects ahead here. Okay. So I think I better wrap it up, given the time that we have. I'm already 10 minutes over time, which is not too bad. Julie, you can shout at me now and say, Kristain,
Okay.
Wrap it up.
Does anyone
Is it feasible to transport the carbon dioxide into space and then convert it in space?
That's a very, sorry for laughing, I'm not laughing at you, it's thinking out of the box. I was just, I haven't really thought about that, I have to be honest. I think it will probably not be a good solution as long as we are still, as long as we're still using fuel to drive our rockets out of the gravitational field of the Earth. We could build an extremely tall chimney, potentially. I'm not sure that's going to work either. No, I think overall the answer would be no. I don't think it's going to work. Prove me wrong. Send me an email once you have shown that it works, and I'll be happy to say I was wrong.
What would the carbon dioxide do to like the moon? Like if we really did, I know it's not possible, but still.
Yeah, that's a good question. Again, I haven't been to the moon yet, and I don't think it'll do much. The problem is that a potential problem would be that the pressure is very low on the moon, right? So you wouldn't be able to store CO2 at any meaningful density. I think that's the best I can get, the closest I can get to an answer in this one. I'm sorry if it's not what you're looking for.
Anybody else? Yeah.
You described how we can get CO2 out of the atmosphere and sort of contain it. Do you think it'd be possible or feasible to do that with other greenhouse gases like methane or nitrous oxide, and then maybe do a similar containment program?
Well, I mean, I think the yeah. But I think I know that the other gases are potent also, but I think where we really have a chance to make a difference is on the carbon dioxide part, because we are the main source of producing more CO2 by burning fossil fuel, coal, oil, gas, etc. So you could potentially separate all the gases from, but the main sources of CO2 in our case, in our case, is power plants and cement industries, etc., where we have a high concentration, a large amount, and it's an easy task then, or an easier task, to separate it and inject it into the subsurface. So with respect to the others, I mean, methane, if we emit methane from any operation, we would love to capture it because that is a commodity and we can use it to generate energy. But the man-made sources are primarily from power plants, etc. So that's where we would start out, I think. So I have time for one last question. Then I'll have to. It's my turn to babysit. So I'll hand it over to the next speaker.